When OLED displays emit precise colors, or industrial catalysts accelerate chemical reactions, you are looking at the macroscopic physical expressions of microscopic quantum mechanics. But translating quantum mechanics into physical materials presents a mathematical wall. For molecules larger than a few atoms, the electronic wave function becomes too complex to solve exactly. To bypass this limitation, material scientists approximate electronic states using molecular orbital theory. They construct models of complex molecules by treating their states as linear combinations of individual atomic orbitals. This Venn diagram outlines the three strict mathematical conditions that must be met for these atomic orbitals to mix strongly and form bonds. The first two requirements define physical proximity. Orbitals must be close in energy and physically overlap in space. The final condition is the ultimate gatekeeper, matching symmetry. If spatial symmetries clash, they will not interact. We will explore the three structural pillars that leverage this symmetry requirement to engineer physical properties: symmetry-adapted linear combinations, conjugated pi systems, and ligand field theory. Understanding molecular symmetry provides the exact mathematical rules that are required to design the color, magnetism, and conductivity of modern materials. Atomic orbitals describe the probability of finding an electron, and electrons behave as waves. Therefore, orbital interactions are dictated by phase interference. These wave patterns show the mechanics of orbital mixing. When phases align in perfect sync, they produce constructive, symmetric combinations. When phases oppose each other, they cancel out, resulting in destructive, antisymmetric patterns. To apply this to an entire molecule, scientists build symmetry-adapted linear combinations, or SALCs. These are specific, mathematically allowed orbital combinations that perfectly match the geometric symmetry of the entire molecular structure. In this diagram of the water molecule, the two outer hydrogen 1s orbitals combine into symmetric and antisymmetric SALCs. The central oxygen atom acts as a strict geometric filter, only accepting interactions with hydrogen SALCs of identical spatial symmetry. If spatial wave patterns conflict, the math is absolute. The overlap integral for a symmetry mismatch is exactly zero. A zero overlap integral dictates that no chemical bond can physically form, regardless of how closely the atoms are positioned in space. Orbitals acting as strict symmetry filters provides the exact mechanism that limits chemical bonding. This binary rule set forms the baseline for constructing highly complex molecular architectures. When we scale this logic to large organic molecules, simple two-dimensional structural diagrams fail to explain their unique stability and optical properties. As shown in the top section of this graphic, simple drawings of alternating single and double bonds do not accurately represent how electrons actually behave in these carbon chains. The reality is driven by conjugated pi systems. When adjacent carbon atoms have overlapping p orbitals, they merge to form continuous pi molecular orbitals. This causes electron delocalization. The electrons are no longer confined between two specific atoms. They flow smoothly across the entire conjugated chain. This chart plots the boundaries of this system. It is defined by the highest occupied molecular orbital, the HOMO, and the lowest unoccupied molecular orbital, the LUMO. The energy gap between these two states dictates the molecule's behavior. This matrix compares ethene, butadiene, and hexatraene to demonstrate the conjugation length rule, directly linking the physical length of the carbon chain to the size of that energy gap. As the number of conjugated carbons increases from 2 to 6, the spatial extension causes the HOMO-LUMO gap to steadily shrink. A smaller energy gap means the molecule requires less energy to excite an electron across it. This physical shift allows the molecule to absorb lower energy light in the visible spectrum. Extending the physical carbon chain is the precise mechanical adjustment organic chemists use to tune a clear molecule into a highly conductive semiconductor or a vibrant organic dye. This precise control over energy gaps extends beyond organic carbon chains. Scientists apply similar spatial geometry constraints to inorganic transition metal coordination complexes. This diagram plots an isolated transition metal ion with 5 equal degenerate d-orbitals. As surrounding ligands approach to form bonds, their electrostatic repulsion breaks this perfect symmetry. In an octahedral field, ligands approach along the axes, forcing directly aligned orbitals into a higher energy state, creating an octahedral splitting pattern. The exact size of this created energy gap determines electron configuration. It dictates whether electrons remain unpaired, resulting in a high-spin magnetic state, or pair up in the lower levels to create a low-spin state. This side-by-side comparison proves energetic splitting depends entirely on spatial geometry. By reducing to 4 ligands in a tetrahedral layout, the splitting pattern reverses entirely. Fewer ligands and less direct overlap result in a significantly smaller energy gap. Manipulating the exact three-dimensional spatial geometry of surrounding ligands provides the control needed to dictate the specific photon energies a metal can absorb. It is the direct mechanism for engineering a material's magnetic state and visible color. In applied material science, these 3 pillars are not used in isolation. Designing advanced technologies requires synthesizing them into a single molecular system. This schematic of an OLED emitter synthesizes these quantum blueprints. The outer conjugated pi systems are calibrated to tune the energy gap, dictating the display's emission wavelength. At the core, Ligand Field Theory at the Transition Metal Center manages high-efficiency electron states and spin-orbit coupling. And binding this entire architecture together is the strict symmetry-matching logic of SALCs, ensuring all components interact exactly as intended. Symmetry limits orbital interaction. Delocalization tunes organic energy gaps. Spatial geometry splits inorganic metal states. By mastering the mathematical and spatial rules of molecular orbital theory, material scientists dictate macroscopic reality. At the quantum scale, molecular geometry is technological destiny.